In this video we'll look at arrays. This is section 10.2 of the CIE 9618 Computer Science A-Level course. So we want to be able to use array terminology, select the right kind of structure for our task, be able to write array pseudocode, and to carry out sort and searches using arrays. So why do we use arrays? Arrays are extremely useful in programming. Instead of having to define multiple variables for the same purpose, we can just define a single array to hold them all. For example, if you want to hold the names of students in a class, you might need 20 separate variables or more. With an array, you just need to define one thing, not 20. This saves programmers time, but it also allows the data to be processed easily. So some of the terminology we use with arrays and a definition to start with. So an array is a fixed length structure, it's a data structure, holds several elements but of the same data type, and each is reached by a consecutive index. So we have a lower bound, which is the first index value, in this case 1, but can be 0, and an upper bound, and the last value there we have is 7, that's our upper bound. And then index is a subscript, the position that we want to access. For example, if we talk about element 4 with an index of 4, then it's number 41. As I say, in CI pseudocode, it doesn't actually assume the lower bound is going to be 0 or 1, so you should always specify which one you're using. They do typically tend to have 1 as lower bound in their questions, but your answers could be either and algorithms could be either, so you have to be really careful and check which lower bound they're using. So you have 1D and 2D arrays, one-dimensional and two-dimensional arrays. You can go further, obviously 3, 4, 5 and wherever you want, but for the course we only really need 2, up to 2. So a 1D array is a single list of related values. One index is enough to locate any element you want. For example, test scores in a class, daily temperatures, or names on a register. They could all be stored in a one-dimensional array. In a two-dimensional array, then it looks like a grid. You have two indices, row and column effectively, and you need both of those to locate any particular element. That might be good for anything that's like a game board, a noughts and crosses board, seating plans, a spreadsheet style table of results. So you need to be able to choose whether you need a 1D or 2D array, but it's usually quite obvious based on the question. So in pseudocode, in CIE pseudocode, we can declare these kinds of arrays as shown here. We use the word declare as normal and a variable name, then the colon, but then array, square brackets, the lower bound, colon, and then the upper bound, and then close the square brackets. And then we have to say what kind of data type all of the elements in that array would be. So here, for example, we've got of string, and we've got of char. So a one-dimensional array, you just need one set of lower bound, upper bound, but in the two-dimensional array, you need two sets. So we've got 1 colon 3, 1 colon 3, so that means there are 2 dimensions, each of which has 3 items, so 3 index values. So a 3 by 3 grid in that case, i.e. 9 elements in total. We always specify a lower and upper bound. If we're doing pairs, and then in pseudocode, CIE pseudocode, we do the two sets separated by a comma, and every single element, regardless of whether it's one-dimensional or two-dimensional, would be the same data type. So they all have to be strings or all chars. That's a restriction on arrays. Note that lists in Python, for example, are not restricted in that way, and they can have mixed data types. But arrays, strictly speaking, are the same data type. So we can process arrays. As I said, it's both easier for programmers to create them and not have to specify dozens or hundreds or thousands of variables of the slightly different names, but it's also easier to process the data once you've got them in the array. So if we want to traverse a 1D array, then we just use a counter. We know how many items are in there, so we're using a for loop, and we just say something like for indexes 1 to 30, and then go through each one. So it's very easy using that index to look at every single item or look at any particular item that you want. And then if you want everything in a 2D array, you can go in any order you want, but it's typical to go row by row, and then within each row you go by column. So in this case we need a nested loop. The columns loop within inside the rows. So for every single row it will go through every single column and then output the element at that row and column position. So one of the things we might need to do with data in an array is to sort it. And one of the simplest sorting algorithms is called bubble sort. Bubble sort works like this. You start with the beginning of the array and you say, are the first two items in the right order? In our case we've got 5 and 2, and if we want ascending order they're not in the right order, so we need to swap them over. So we get 2, 5, 8, 1. We then move on to the next position, which starts at 5, and we compare 5 and 8. They're in the right order already, so no swaps are made. Then we move on another position, and we compare 8 and 1. They're in the wrong order, so we swap them over to give 1 and 8. Now we have 2, 5, 1, 8. We've got to the end of the array, but our data's still not sorted. We've only completed one pass. We need to make multiple passes to ensure that the data is in the correct order. And in fact, after one pass, we can guarantee that the last position is correct. After 2, the last 2 must be correct, and after 3, the last 3 must be correct. And if the last 3 are correct, then all 4 must be correct, because I only have 4. So we can actually do this process by making the right number of passes, which is the number of items minus 1. If I make 3 passes in this case, I'm guaranteed to get the data in the right order. So this is the bubble sort version 1, where we do just that. We've got 2 loops in this algorithm, an outer loop and an inner loop. The inner loop will go along and compare every item in the array, swapping them over if necessary. The outer loop repeats a whole pass the right number of times to guarantee that the data is in the right order. And you can see that the number of times we need to do that is n minus 1. In our example we had 4. If we do 3, we can guarantee that the data is in the right order. And the inner loop is also to n minus 1 because it's comparing this item with the next one. And when we get to the end of the array, there's nothing after it to compare with, so we have to stop one short of the end of the array. Okay, this is version 2, which is more efficient. Because we can stop when no passes are made in a pass, we're going to use a Boolean flag, a swap flag, to indicate when that happens. So if we can get through an entire pass of the array without making any swaps, we know that the data must be sorted and we can stop the algorithm. So this is how the code works. We replace the outer for loop with a while loop, and we set swap to true at the beginning, and we continue if we've made a swap in a pass. So we say while swap equals true. Obviously to begin with we have to assume that we have made a swap even though I haven't done anything yet, just to make sure that the loop actually occurs, and we go into the code. But the first thing we do within that while loop is set swap to false to reset it, so that we can say if we can get through that whole pass without setting it to true, it's still false when we come out, then we're going to stop. The inner loop's the same, so the pass itself is the same. We're going to use our for loop. However, instead of going for 1 to n minus 1, we're going to go for to n minus I, and we start with I as 1, but as we go through a pass, every pass, we're going to increase I and therefore reduce the number of items we have to look at. So this is another efficiency saving, right, where we make it better because we don't have to look at every single item in the array each pass, because we know that after each pass one more of the items is already in the right place. So basically ignore the end of the array, and the end of the array that we ignore gets bigger and bigger as we make more and more passes. The rest of it's very similar. We check if they're in the right order. If they're not, we swap them round. And if they're not and we swap them, we set swap to true, because even if we only make one swap in a pass, we need to make another pass just to make sure that we can go through all the way through without making any swaps. Another thing we might need to do in an array is search for an item, and a linear search is the most basic form of that. So linear search checks each element in turn, starting from the first one until it finds the target value or runs out of elements, i.e. it gets to the end of the array. So it works on any array whether it's been sorted or not, but it can be really slow for large data sets. So in our example we have index values from 1 to 7, and we're going to start at 1. It will check and compare that value. So the value at index location 1 is 12. It will compare that with what we're looking for, which is 41 in this case. It's not that, so we move on to the very next index value, which is 2. It's not that, we move to 3. It's not that, we move to 4, and that is 41. So we're going to stop there, and we don't need to look through the rest of the data 5, 6 and 7. So the linear search checks elements one at a time in order, and there's no assumption about how the data is arranged. It can stop immediately once a match is found and not check the remaining elements. The only exception to that is if you actually want to find all of the occurrence of the number, or try to find all the occurrences, so then you can carry on. So for example, you might be counting how many occurrences of the number 41 there are. And then if you get to the end of the array with no match, we know for sure that the target is not present. So in pseudocode it would look like this. We set our index value. Remember, we're using a condition control loop here because we don't know when we're going to find it. It's repeat until. We set found, a Boolean variable, to false. That means we haven't found it yet. And because we're using repeat until, which is a post condition loop, we're guaranteed to always go into the code at least once. So we go through from index 1 and we compare each value in the array with the target value. If it's found, if they match, then we set found to true, and that means that we can exit that loop when we found it. But we also need to exit that loop if we get to the end of the array, and that's the second part of the condition there, the OR index is greater than n. So if it becomes greater than n, it means we'd be referencing an element that doesn't exist, and we can't do that. That would cause a crash. So we have to exit the loop under that condition or when we find it. And then afterwards we can determine whether we have found it or not by checking our Boolean found variable. So some key takeaways from this. Arrays are a data structure that hold multiple elements of the same data type, and they are fixed in size, at least for CIE, that's what they say. We have an index, which is a number, an integer number that indicates which element you were interested in. An element is the actual value within a particular location. We have the lower bound, which is the first index value, and an upper bound, which is the last index value. And remember that arrays could be 0 indexed, i.e. the lower bound is 0, or 1 indexed, where the lower bound is 1. And we can have 1D or 2D arrays, and you need to choose the right one for your particular problem. So to declare an array, we use the word array, square brackets, then the lower bound and the upper bound separated by a colon, closing the square brackets, and then we have to say what data type those elements are going to be. So we say of whatever type you want. And we can use loops to traverse. If we want to go through every single one, we can use a for loop and just make sure the index value goes from the lower bound to the upper bound. If we're doing 2D arrays, then we can use nested loops to look at every single item. And we might need to sort an array or search an array, and bubble sort is a simple sort that we could use that repeatedly swaps adjacent values until the whole thing is in the right order. And a linear search checks each element from the beginning, from the lower bound, until you find the item or you got to the end of the array. Okay, that's the end of 10.2.